Welcome, my friends, to Gabversity, where facts don't care about your feelings. Alrighty, welcome to Gabversity, where you can go fact yourself. And now we are doing some heavy mathematics, and this is to help us map out how to find quantum particles. And this is our last notes about the Christian thing and the liberal thing and all that. We can move that along. Welcome back to Paint Something Scott, to L. Brooks, to all our other students, Damien White. Welcome to all of you. So, I'm just going to show you where we started from and where we're going. Boogie Bumper, hey, hey, the Aussie. All right, so, hey, hey. Remember, hello, my dear. Here, this was the Schrodinger equation in 2 dimensions, being 1 time and 1 is 1-dimensional space. If you're not sure on that, you can look at the last few lectures, and we are continuing. And yesterday, I showed you that because that equals that, and they're completely 2 different entities, that means that they must be a constant between them. Just like we said, if you remember yesterday, we said that if there are 2 cars on the highway, if they're able to talk to each other, then they must be going at a constant speed, right? Otherwise, it would never work, right? I know you could have a constant acceleration, but that wouldn't help my analogy. So that's what happens in mathematics. So let's go back to it. So what we said was this and this are traveling at a constant speed, which is this something. We called it E. Lotto draws. You know, a mathematician won the lotto like 3 times in a row. How convenient. Tang Frank. Hey, hey. All right, so firstly we're going to look at this side. This is the time side of the equation, and this is the space side of the equation. Because as we said, this is 1-dimensional space, and this is 1-dimensional time. But we know that time has multiple dimensions, and so does space. But we won't get into that yet. We'll get into that later. All right, so now let's just look at this side, okay? I'll show you what we're going to do, all right? So this side, this liberal business, forget that. That was from Gabsmacked. Okay, so now let's just write out that side again. From, now I forgot what it was. It should be I, H bar. Oh, my thing is running out. 1 over psi, 1 over phi, sorry, and then it should be d phi dt. It is, yeah, d phi dt. Right, and then d phi dt equals that constant. So that's one of the sides, as I said. Derivatives, hey, hey, welcome back, Biscuit. Yes, derivatives. So now it's just basic integrals of this. So if you remember, I told you guys before that you have integrations going backwards. So this is sort of the speed, because it's this function over time, which is like speed. But what we're going to do is we're going to go back to distance, and we do that via integration. All right? So as I said before, if you derive a distance over time, you get the speed. If you integrate speed with respect to time, you're going to get back to distance. And that's the mathematical version of what I just said. All right. So now what we're going to do is we'll put the phi over there, right? So we'll times everything by phi, basic algebra, and we're going to get I, H bar, right? Alternate dimension number, pixel of the universe, d phi dt equals this constant thing multiplied by phi, right? So we just rearrange that equation. The next thing we're going to do, my awesome brothers in the house, always a pleasure. All right, the next thing we're going to do is we're going to put this dt over here. So what that is, basically, it's like, you know how that thing there is basically the analogous to speed. So speed is miles per hour or kilometers per hour. What we're going to do is we're going to keep the miles or kilometers on one side. We're going to push the per hour to the other side, right? And in math you can do that, which is pretty damn awesome. Actually, to make it clear for those who are not mathematically lessoned, let's just say, have not been schooled in maths, it's like saying, you could say 1 plus 1 equals 2, or you could say 1 equals 2 minus 1 by taking one of the ones on one side and I'll actually show you. I'll show you. All right, this is basically what we're doing. You could say 1 plus 1 equals 2, or this could be 1 equals 2 minus 1, right? Because we just put that 1 on the other side and you make it a negative because it's the anti-version. It's like a seesaw, right? So to keep the seesaw balanced, that 1 over there becomes a minus 1, right? And that's all that's happening here, but it's with times and divide. So this dt is going to go up there, right? So I, h bar, right? Alternative dimension, h bar, which is the, what do you call it? The pixels of the universe, right? D phi equals, right? Equals E, right? Phi dt. Okay. Now all we have to do is put this phi back here, which we didn't have to do that, and we normally wouldn't, but I'm making it simple by taking each step at a time. So now we put that back underneath again. So now, and then we're going to put, well, we could put that there, we'll keep it here. So we now say IH d phi over phi equals E dt. All right, so all we've done is just rearrange that equation to make it look like this. Now, why have I done this? Because once again, we've done the same thing. We've now put this on one side and this on the other. We've now, originally, we took the whole multi-dimensional equation and we put everything to do with time on this side, everything to do with space on this side. Now, what we did was we took only the time side and then we split that up as well. So we split something that was already split, and we've now put all of the phi's on one side and the dt on the other. What is that? What have I done? So originally what we did was we ripped apart the wave, and we have the time on one side and the space on the other of the wave, right? Of the wave function. Now what we've done is we've taken one of the sides, which was the time side, and we split that up. So for example, let's say instead of saying meters per second, like on one side we had meters per second, on the other side we had distance per meters, or something like that, right? And then we got rid of the distance per meters, and now we're only dealing with the time section, which is like meters per second, which is speed. Then we want to integrate it, and we just want to get the distance. Now, what we do to do that is we took the per second and we put it on the other side. So now when we integrate, we're going to get the speed on one side and time on the other. And that means that you'll have a distance for every snapshot of time. And then we can take one snapshot and you'll see it now. That's basically what we're doing now in the mathematics, right? So now we need integral calculus. So here, right, here is the integral. We're going to say that the integral of this, we're going to integrate both sides. So we want to integrate IH bar partial derivative psi over psi, okay, d psi, because we're integrating with respect to psi, okay, equals, right, the integral of E dt, because the dt is already there, right? Actually, the d phi is already there too. Sorry, I didn't have to add that. All right, stupid mistake. Okay, so now all we have to do is integrate. Now these are constants, so they can just go outside. This is now integral calculus here, right? It's just basic integral calculus. So that IH bar outside of 1 over psi d psi, which is the same thing. That's just 1 times that, puts that on top. So that's the same. Equals, and then that E is a constant. We don't know what E is yet, right? It's something. It's just some number, right? E dt, all right? Now we integrate both sides. Now here we're going to have IH, right? IH ln, which is the logarithmic function, ln psi, okay, plus some random constant. Now this here is just what's the solution equation and best way to get a girl to forgive your genius style. A lot of practice. So I went out with a lot of girls and I made a lot of mistakes, and a lot of girls hate me, but it means that a lot of new girls like you because you don't make the same mistakes. So it's sort of weird, because then you realize that when girls like you, it's only because you're doing the right thing as opposed to who you are, and they think it's due to who you are. So we integrate this and we're going to get ET ET, that's funny, excuse me, it's so freaking windy in Gabversity. All right, so we're going to get ET plus another constant, right? So now what we have, these constants can integrate, so we don't have to worry about them, and then we can make phi the subject, right? And I'm not going to show you mathematically how to do that, because that's just basic maths, so either you know it or you don't. But basically, if I rearrange this, where's D? when you integrate, this is dt. That means with respect to time. When you integrate, you just have t, because that's the opposite of the derivative. The derivative of t is dt. So I'll actually do it again. So if you want to derive x, right, the derivative of x, so in other words, the derivative of x with respect to x equals dx, right? And so if you integrate dx, you're just going to get x plus some constant, right? So it's just backwards. So derivative of x gives you dx, integral of dx gives you x plus some random constant, all right? That's what happened to the d. Okay, so now if we rearrange all of this, which I'd advise someone, if you do well in maths, then do this at home, because it's really fun, but you'll end up getting phi of t, okay, equals some new constant, right, which is a combination of the other constants and something I won't show you, e to the minus t, e, that's something e, okay, over h bar. All right, so this is now the new equation. We finally have the equation for phi. So what that means is that we have now been able to map the equation for time for a quantum particle. So what that means, and I'll show you it again, all right, we can map what happens to time with respect to a particle, okay? So what does that mean? Well, that means that if we have the time, right, then we know, and we already have this because that's the size of the pixel, then we can figure out what this something is. If we have this, this, and this, then we can find out what this is. Or if we have all of these, we can find out what this is, right? That's only the time section. So that one there can tell us the flow of time, or it tells us at what times something will appear. It's an amazing map, and that's basically how we do that. All right, so now I'm going to show you. So that's, you don't have to actually remember all this. In the end, you're only going to have to remember one or two formulae, right? But this is important because if you look at how it's done, it actually helps you remember the formulae much easier and get at least roughly what's going on when we look for particles. Because I could start right now. I could say to you, let's go find a particle, and we'll do the equation and we find the particle, right? And then you'll be like, why am I doing this? You still probably think, why am I doing this? All right, so the next part is the stationary state. Here we go. So the equation in 2.5 is the time-independent Schrodinger equation. We can go further until the potential of Vx is specified. All right, and I showed you that before. Here is the time-dependent Schrodinger equation. Let me find it. The time-independent. Time-independent is right here. Right? This section here is time-independent. Okay, so that's the time-dependent, which we just did. This is the time-independent. All right, that means that we don't need time to figure out what's going on. We know that we have some constant, right, that this is equal to. We have the mass of the particle. We have, you know, the size of the pixels of this universe. We have the actual wave equation, and we have the derivative of the wave equation and the potential energy. All right, so if we are missing one of these, we can find the other one, right? And that tells us that there is like getting the, you know, as I said, you get the skipping rope. Imagine that you freeze time. You freeze it, and then you can zoom around the skipping rope and see that snapshot of the skipping rope, like a 3D photo of the skipping rope. So you can see exactly all the possible points that the particle can exist. So the particle will never exist. For example, you know, if you're looking for your phone, if you have a certain equation and you freeze it, you know that given this time of your life, like let's say, you know, Wednesday, your phone will never be in North Africa. It'll never be in North Africa. It's impossible. It cannot ever be there. If you find a phone in North Africa, it's not your phone. That's basically what we're doing, right? All right. So, okay. Here are the stationary states. Why is this important? Well, if we want to find stationary states, right? Here is the actual full equation. A full equation with the capital psi, which is xt. All right. X is one dimension of space. That's one dimension of time. So this is the baby version of the formula, which we haven't gotten to the full one yet.
But the baby version works in the same way. It's one dimension of space, one dimension of time. So it's a two-dimensional wave, right? Which sort of looks really weird, but it's pretty cool. It's a solid wave.
If you were to see that wave in real life, it'd be a skipping rope that went this way and this way at the same time. So maybe like trying to think what it would look like. It's sort of like, instead of having a skipping rope, you have a blanket, right? So it's like a blanket that's moving as opposed to one skipping rope. Okay.
So actually I can draw it for you, right? Let's say you have, right? You have a skipping rope and in something like this, right? But what happens is that the skipping rope becomes two-dimensional. So you have this, and you have, okay? So now you can see that, can anyone actually see that? That's like a sort of like a, I don't know, like a blanket that's moving up and down instead of just one line. And that means that over time, and this is like the this would be the second dimension, time this way, right? You would see that this particle could be here, but in the future, right, this blanket might be wobbly. So the blanket sort of might go higher in this section here in the middle. And so the particle in the future might be located in a different location. That's the two-dimensional version. But what we want is, we want a snapshot. We want to slice this down and just get one line. That's what we're trying to do. So this one, right, if we just look at, let's say, lowercase, just of x, right, it'll look like this. It'd just be like that, right? You wouldn't have the extra dimensions. I hope that makes sense to people. Okay. So now what I said was, we have capital of xt, so that's the capital wave function, right? That's the baby multidimensional function which has space and time, equals, okay, lowercase, right? So that's the one-dimensional wave in distance multiplied by the time version, which is e to the minus I e over h bar. Now we got rid of the c. The c is hidden in here because the c is just a constant, so it doesn't really matter. We absorbed it. Okay, and what that means, that instead of the wave being here, it might be up a bit or down a bit. It's the same thing, roughly. All right, now why is it that by that? We'll have a look. This is what we did right at the beginning yesterday when I showed you, if you remember, in this universe, this two-dimensional wave is made up of the one-dimensional wave of space multiplied by the one-dimensional wave of time, right? That by that. So that here, today we converted into this, so it's the same thing. We've just done now this and this. So we haven't really gone that far. We've just converted this into looking like that, right? And to do that, we just found the psi function and converted it into what it means in terms of this weird constant and h. Okay, there should be a T somewhere. There should be a T there. All right. So, well, here's something that's interesting. If we want to square this wave, right? A plane. That's exactly right. Tony comes out with one word and kills it. That's exactly right, my friend. All right. So here. Right, we have xt. Now here's an interesting thing. Remember how I told you guys before, if we were looking for your phone, we had to square the wave function so that we can find the probability of locating your phone. Here's something interesting that happens when you square the wave function. When you square it, that's the same as squaring this, right? And that's the absolute value squared, right? No Tifa. All right, so when we square the wave function, whoopsies, sorry. It is exactly like doing this. We take the absolute value of that, right? And we also the absolute value of the other thing, and we also square that too. So minus I e t over h bar, all squared. What happens with this? Well, with this, that's the complex number, right? That's the alternate dimension, which I've showed you before. In complex numbers, when you square the absolute value, you actually get 1 in this case, and you're left with this squared, right? Which equals, right? you're left with the absolute value of that squared. Now this is I complex, exactly. Tony is on a roll, my friends. I love how you're called Scope Watcher. That's hilarious. All right, so what have we done? Why is this important? It's freaking important because now when we want to normalize a wave function, we only need the spatial dimension. We don't need the time dimension, because whenever you square the time dimension, because it runs in a parallel universe, when you square it and you take its modulus, you take its absolute value or modulus, it disappears, right? Which means that you don't need to know the time to figure out the location of the particle. That is unbelievably brilliant that the physicists came up with. That somehow you can locate a particle independent of time itself, which means that you don't need to know the time to figure out where the particle is. Brilliant stuff, absolutely brilliant, right? So, all right, now let's move on. Okay, where are we? Every expectation value is constant in time. Why and how? Because if you've ever, this one I won't talk about in this lecture. This is why I really should do a maths lecture, but I just don't have time. But if we get more subscribers and more book sales, I'll definitely dedicate myself to doing this. Why do you not need time? Because the answer is in complex maths. And basically, every complex number has something called a modulus, which is sort of like its real component. And when you take the real component, Jesus Christ. Oh, that's funny. No, it's actually not a maths lecture. Maths is way more complex. But it's not complex. It's only complex because you probably didn't have a good teacher, right? Like, I'm not teaching you maths. Yeah. If I taught you maths from the ground up, you would kill it. I'm telling you. Like, I've seen you, like your comments, Boogie Bumper, and stuff you said to me in Gab Smack. It's obvious that you're extremely bright. So if I was to teach you maths from the ground up, which would take 2 years, right? So I can't do it, but I've done this before with people who are really bad at maths, and I've taught them for 2 years and they've become really good. Like, you'll never be a maths genius, but you will be really good at it, right? It's like, you know, people, if you speak English your whole life, you might still only be half articulate, right? But you can still speak the damn language. And it's the same thing with maths. It's a language. That's all it is. Anyway, if you do complex analysis and mathematics, which is like 2nd or 3rd year maths at university, right? Not just complex numbers, but complex analysis, you'll be able to prove that squaring the modulus equals 1 in this case, right? And it only happens in this particular subset of complex numbers in physics. So the physics in this universe, because when you study mathematics, you study the theoretical physics of all universes, of all possible universes, right? In physics, you're only doing one infinite little subset of mathematics which focuses on the laws of this universe. All right. So basically, that's the answer. The answer is when you take a modulus of a complex number and square it, it turns out that in this universe it always equals 1, which is amazing. What an amazing coincidence that in this universe that's what happens. And you can have two arguments for that. You can have that there are infinite amount of multiple universes, and whenever you have an infinite amount of multiple universes, you're going to get one that's just right. That's just mathematics. The other thing, some people think that it's God. So one or the other. I'm not here to argue that. That's not Gabversity. Gabversity says, fact your feelings. Feelings, go fact yourself. All right. So let's move on. So let us keep reading our lecture notes. And I'm very lucky that I did a mathematics degree. I'm so glad I did it. Otherwise, physics would have been so much harder. All right. So the same thing happens in calculating expectation value of any dynamic variable. Okay. So the point is that any dynamic variable wipes out time. So they're assuming that you don't know maths, and they're telling you that whenever you have a dynamic variable, right, then time gets wiped out. And that means like what I just said. Okay. Reflexes of a steel trap. Hey, Danny, your pizzas are still here, man. Come and eat your pizza. No, I'm not having pizza, bro. All right. Jeez, man, this fucking wind. It's crazy. All right, so let us move on. Every expectation value is constant in time. So what does that mean? That means if I look for my phone in my house
right? If I expect my phone at 12 o'clock to be somewhere, it's obviously at a certain time, right? And it's frozen in time. Okay. Now, so we can drop the time factor. And what I said is we simply use the wave function that's not a capital. It's the wave function that only uses space. That's what we've said. And people confuse them. So we have to remember you've got the true wave function, okay, and the non-true or fake wave function. So the fake wave function is basically the function without time. It's not the full story. Okay. Time dependent factor in particular is constant, hence nothing ever happens in a stationary state. All right. So in stationary states, nothing happens. That's exactly right. So in other words, if I take a photo of, if you take a photo of your neighbor driving their car, in the photo, you just see the car. You don't know how fast the car's going. That's why for speed cameras and stuff, you need two photos so you can do a comparison. And that's the same here. When we find the location of the particle, you can never know its speed. And that is why you have the uncertainty principle. You cannot know a quantum particle's location if you know its speed, and you cannot know its speed if you know its location. You can only approximate. And that is phenomenal, right? Down at that level, no one can know what's going on because it's the fundamental particles that make us up. So it's hard to measure yourself in a way. It's like trying to pick yourself up off the ground. You can't do it. All right, so there are states of definite total energy. Okay, what do I mean by that? You guys know, if anyone's done classical like high school physics, right? You have kinetic energy and potential energy, right? So if I'm holding my watch, what book you have there? Oh, yes, good question. The book, you can get it for free off the internet. It's a PDF book and it's called Introduction to Quantum Mechanics by Griffith, 2nd edition. Let's say I have this phone. Hello. If I have this phone and I drop it, if I let it go, it's going to fall, right? Because it's got potential energy. But there is another state. Let's say I let it go and it falls and I take a photo here, right? It's still falling, right? But it's also moving. So the total energy state is the moving energy, kinetic energy, and the potential energy that's still left, that's still pulling it down, all right? Those two energies, right, in classical mechanics is kinetic and potential, right? In quantum mechanics, right, it's called, and this one you need to know, this one, it's called the Hamiltonian, okay? The Hamiltonian, okay? So I'm going to show you what it looks like in classical mechanics, and I'm going to show you what it looks like in quantum mechanics. Gravity is a scam. That's actually true. I like you. You're crazy, but I like you. Thank you. I appreciate that. The crazy part is actually a compliment. Fake news. All right. All right, the Hamiltonian. So here we go. I'm going to show it to you. Okay. So here we have, let me pick a random person from here. We have Carrion Wind. That is so funny. Carrion Wind. Gravity rules, it's our God. Gravity is actually an illusion. It's not a real force. It's a bend in four-dimensional space-time. But we'll get to that another day. All right, so here is Carrion Wind, right? Carrion Wind is at the top of the cliff. Sounds like something Trump would say. Yeah, still a force. Yeah, you could call it. It acts as a force. But under extreme cases, it becomes obvious that it's an illusion. But the effects of it are certainly real. So here we go. This is Carrion Wind, and he holds a ball and then drops it, and then the ball's like. About Harry being a scam. Oh, okay. Yeah, that's true. He would say that, and it would be really funny because people would get triggered, and I'd just laugh. Guys, it's so funny. All right, so he drops the ball. Carrion Wind is dropping the ball like a seesaw. Yeah, that's true, like a seesaw. So at the bottom, we just have all kinetic energy. Ain't the fundamental force of nature? No, it's not. It's actually not. Gravity didn't appear till later, despite the whole planet pulling it down. That's true. Oh, thank you, Papas. We'll do it one more time.
This summer, get ready for carrying wind. All right. So the ball up here, right? This is all potential energy. Okay. Down here, it's all kinetic energy. Alternative facts. This is true. Thank you. Here, we have potential energy plus kinetic energy. Okay. So this total equals the Hamiltonian. That should be an N, sorry. Hamiltonian. All right. Now in quantum mechanics, it looks like this. It's called the H of X and P. All right. H of X and P. There's distance. All right. H of X and P. All right. Which equals, okay, that should be probability density, I'd say, or momentum density. We'll find out. P squared over 2 times the mass plus potential energy of X. All right. Coming to Gabsmacked, coming to a poker table near you. Yeah, my grandfather taught me to count cards when I was 8 and I beat him when I was 11. I still don't know how to play poker though. We've been lied to from day one. It's impossible to wake up. Well, some people get red-pilled. That's life. What is P? Good question. P is the momentum over 2 times the mass. It's the same as this one. Kinetic energy. Kinetic energy equals half mv squared. If anyone's ever seen that, that's the classical mechanical version. Because if you look at it, right, which equals 1 over 2 mass times velocity, right, which equals, yeah, that's a good point, which equals half, right, mass over mass times velocity, right? That is just that, right? Now have a look at this. mv is momentum. That's the definition of momentum. And there's another mv, that's also momentum, which equals half times momentum over m, which equals 1 or times momentum squared over 2m, which equals momentum squared over 2m. Right, so what we've done is that, you see? It's pretty cool. That's another thing about physics. You just rearrange stuff to get other quantities, which is pretty amazing. And that's the potential energy, V of X. So that's distance and momentum. Yeah, that's the definition. All right, so now, if you guys remember from our other lecture, momentum in quantum mechanics, right, is actually implied by this. Planck's constant over I, or reduced Planck over I, multiplied by the operator d dx. All right. There's a lot of, I missed it, damn it. All right, that is that. So all we have to do is put that in here. And by doing that, what are we going to get? We're going to say, therefore, H bar, and we're going to call it H bar for quantum mechanics. It's going to be H bar because it's multidimensional. Right? H bar equals, right, this thing squared over 2m, which is minus H bar squared over 2m, okay, d2 over dx squared, which is the second derivative, right? Okay, plus v of x. All right. Always love that mathematics is the language of nature. Yeah, damn straight. Look, that's a very good point, actually. If you believe we are in a computer simulation, the Feynman method on learning, I have. It's amazing. It's amazing. Yeah, if you've heard of the, what do you call it? That we're in a simulated universe, the people that programmed our universe that we think we're in, the programming language was mathematics. If you believe it's God, then the language of God is mathematics. So either way.
Yes, this is very true. And what's awesome about mathematics is that it proves things before we find them. So black holes were proven to exist before we found them. Four-dimensional time by Einstein was proven to exist before we found four-dimensional the four-dimensional universe. Kurt Godel owned mathematics. Kurt Gödel. Yeah, Kurt Gödel, Alexandre Kolmogorov. These people were freaks, man. Bonjour, Jennifer. Comment ça va de la Canadie? What does four-dimensional mean? Oh, good question. The only way to explain it is how I've done it before, which is you have to pretend that you are in a movie and that the outside of the movie is a screen. So we think we're in 3 dimensions, but we're really in 2. And then there's lots of screens, and that screen makes up a loaf of bread, and that loaf of bread is the 4th dimension that we interact in. Merci, très bien, et toi? Eh, pas mal, merci. Maintenant, nous étudions la physique et le mathématique. Pardon parce que mon français est terrible. Mais j'essaye. Are you a mathematician? Yes, I am a mathematician. I'm a mathematician who is getting into theoretical physics because excellent, merci bien, et enchanté, Jennifer. All right, so alrighty, so let's move on. So now we're going to get a general solution. Now this is awesome. I just tossed my statistic books from years ago. Ever tried reading about Gödel's incompleteness theorem or his other work? Absolutely. I have progressed. That is good. Yeah, these people are amazing. Absolute freaks of nature, man. It's they're pretty good. So now what we're going to do, or of you have hair. Alrighty, let's move on to the more general version of the solution. So you'll see a pattern that keeps repeating. À quelle université? Charles Sturt University, buddy, dans l'Australie. Université de Charles Sturt, dans l'Australie. Alrighty. Yes, Dad. Yeah, mate, Australia, buddy. Oh my God, you have hair. Oh yes, I do. Touch wood. Hello, I'm giving a lecture, but you can ask me.
No, that's right.
Oh, okay.
Yeah, that's right. Just when you get a chance.
Okay, when I finish this lecture, absolutely.
Okay, thanks.
All right. Man, this lecture is going to go for ages. I'm going to have to cut it short. So here is the general solution to the time-dependent Schrodinger equation. Favorite mathematician? Oh, they change all the time, but it's a toss-up between Maxwell, John von Neumann, and at the moment, Alexander Kolmogorov, that Russian freak genius. You know how to push his buttons. Don't you dare cut it short. I'm sorry, I won't. All right, so. All right, phi of xt. This is the time dependent, okay? If it decides to frickin' fix itself, the bastard. Gabversity, man, keeps getting screwed. Where periscope doesn't care about your feelings. Please repair yourself. All right, equals the sum. Now this is where you need infinite series knowledge. To infinity of Cn, and this is psi. Oh no, this is psi n of x, and then multiplied by e minus I E N T over h bar. All right, this here is called infinite series. Now what I'm going to do is I'm going to show you a basic infinite series, just so that you understand what the hell I'm doing, right? But what this is saying here, this is the sum of an infinite amount of waves, and this is going to become way too abstract. So I'm going to show you a very easy version. What's 2? What's 2 equal to? 2
equals 1 plus 1, right? But 2, yeah, absolutely. 2 equals 1 plus a half plus a half. 2 equals 1 plus a half plus a quarter plus a quarter. Right, now I can do this for infinity. I can just keep breaking down the last term, halving it, and keep going, right? So therefore, you could say 2 equals 1 plus 1 over 2 plus 1 over 4 plus 1 over 8 all the way to infinity, right? So you would, if you represented 2 this way, it would be an infinite sum to get to 2, right? And so therefore what you do is you say that j'aime ça. Oh, that's awesome. Mon plaisir, teacher Jennifer. J'aime, what's the word? J'aime enseigner. Hello. All right, so you could say that 2 equals 1 plus the infinite sum, n equals 0 to infinity, all right? As far as I may go. You are blowing my mind. Awesome, man. Infinity of, sorry, let me, 1 over a. Could you do math lectures or some stuff sometime? Yeah, I'd love to. I'm just really busy. The more subscribers I get to Patreon, I need to get more subscribers so that I can not have to work nights. Grade 5's fun for about 10 minutes. That's funny. So what does this mean, right? It's actually, that's wrong. It's 1, n equals 1, right? So what this means is that it's the sum. Tu parles français? Juste un peu, malheureusement. Yeah. J'avais parlé le français, mais malheureusement, j'ai oublié. Yeah, j'ai oublié ça. Something like that. Okay. I have another channel called Sixlang, Sixlang, where I teach French. It's okay. I only learnt it. I spent 40 hours learning it, and then I became a teacher in it. That was 4 years ago. All right, so this here is the same as saying 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 5. So that's actually not correct, because that does not add up to 2. That's a different one. But what you can see is that is an engine which goes for infinity. So basically it's an engine that you're cranking that goes for infinity, and that's what's happening here. So when that equals 0, that's going to be 0. Then the next one is 1 plus 2 plus 3 plus 4 plus 5 of these waves. And that's what this is made up of. That's all we're saying here. All right? So I can't teach more than that at this point, otherwise I'll never finish the lecture. Okay. So now what we're doing, I'm going to show you a miracle. Christians will think it's God, the rest of you will think it's multi-universes. Either way, it's amazing, absolutely amazing. We're going to say this, right, x0. x0 means time is at 0, so this has now become one-dimensional, right? We made time equal to 0. Equals sum of n equals 1 to infinity, okay? So this is the engine we're cranking, of Cn psi of x, okay, n, all right? So this is quite amazing, all right? So what we've done, we've made that 0. Now by putting that 0, this becomes 1. This whole thing becomes 1 because e to the 0 is always 1, all right? So that means that the equation jumps down to this. Now here's the interesting thing. Here's the interesting equation, right? This is what's amazing in this universe, okay? This, right, the multi-dimensional wave equation, xt, okay, which, as we said above, equals the sum from n equals 1 to infinity of all of these terms, Cn, the spatial version, multiplied by e to the minus I, which is the multi-dimensional number, right, times e, n, so this constant of time over h, right? That here, right, the weird thing about it is that that also equals this. N equals 1 to infinity, right? Of Cn, just like before, of the multi-dimensional wave, xt. Now that is absolutely phenomenal, right? That actually works, because mathematics shows you that that does not have to be true. In mathematics, there's a subset of calculus where you deal with harmonic equations, right? Or you deal in complex analysis. It has a word, I forget the word, but basically they are a special type of equations that allow you to do infinite derivatives. I think they're called, starts with C, Cauchy equations, or something like that. I forget, because I haven't done it in a couple of years. But basically what they're saying is that this wave can be broken up into an infinite amount of waves, right? Why is that amazing? That is amazing because that allows you to break down waves, to figure out infinite slices, and then you can compress files. So you can get an approximation. And that's how computer programs work. Because what they do is they take all of the quantum particles and they know that it's made up of waves, but they can, because we don't have the computer hardware to simulate an infinite amount of waves, they can just take an addition of most of them. So let me come back to the 2. Look at this, right? Remember how I said 2 is made up of this? 2 is made up of this, right? What's 1 plus a half plus a quarter? Who knows the answer? Who knows 1 plus a half plus a quarter? Does anyone know the answer? One plus a half plus a quarter. The answer is 1.75, right? Now 1.75 is close to 2. How about next? How about 1 plus a half plus a quarter plus an eighth, right? That's approximately 2.8. How about 1 plus a half plus a quarter plus an eighth plus 1/16? Then it's like nearly 2.9, 1.9, sorry, right? Not 2.8, 1.8 and then 1.9. So you're getting very, very close to 2 the more of those infinite sums you add, but you don't have to add the whole lot. And that's how you can compress files, by getting an approximation that's so close that it looks almost like the exact number. All right. So I'm going to show you an example, and then that'll end today's lecture. And I'm going to have more lectures later today on quantum mechanics. It's going to get more complex. Yeah. Okay. So let's imagine my sound continues to lag. Yay, isn't this the same number according to basic maths? Close. Yeah, it'll be close. You love this stuff. That's awesome. Welcome aboard. Like 0.99999 equals 1 can be proven by algebra. Yeah, something like that. So you could cut it off just after 4 decimal places to save room on your hard drive, for example. Yeah. So now we're going to do an actual problem, and then that'll end today. So this is used in quantum computing. Yes, it's used in heaps of stuff. It's used in MP3s. That's how MP3s were invented. That's how Apple was able to invent that sound file 3GP. 3GP by Apple was invented by that. Security like for credit cards was invented by that. Post your Patreon link. Oh, thank you. It's on my YouTube. If you go to YouTube, you'll see it in the description. I'm straight, but you make me rethink. Oh, well, I'm straight, so you don't have to worry about that. But thank you. If you go to Gabsmacked on YouTube, GABSMACKED, Gabsmacked, you will see that I post these to Gabsmacked, and then there's a description, patreon.com/real Gabsmacked, and then you can subscribe, and then you'll get even more videos. There's a lot of private videos that I have just for my Patreon guests, and we're going to build it up. The more I do, then I'll be doing heaps more of this, obviously, and I'll dedicate it to you guys. All right, let's do a problem, and then we're going to go. Okay. So here is the problem. Let's make a very, very simple equation. X, right, 0, okay, and it is psi, it's a lowercase psi. Oh no, it is capital. It's capital psi equals C1 right, psi of 1x, so that's one stationary wave plus another stationary wave, right, which is this one. All right. So these, let's just say we have a really simple particle and it's made up of two waves. Normally they're made up of millions and millions of waves, right? That's how we get quantum particles, right? But let's just say we have one like this to make it easy. Okay. Now, what is the wave function? The question is, what is the actual, how do we rebuild the wave function, right, at subsequent times? And then we have to find the probability density and describe its motion. So this is the really awesome thing. We are just given a snapshot. We're given a photo of a quantum wave function. And we have to recreate using mathematics the full wave function over time, right? So it's like someone took a photo of your phone in your room, right? And then we have to recreate over time where that phone will be located throughout the house, throughout the week. That's what we're going to do now with mathematics, right? It's just phenomenal, the stuff that we can do, right? So here we go. Okay. So the first part, right, is we're just going to recreate it, which is easy. All we have to do is say, okay, well, that of xt, we're now rebuilding it. So that one has no time. That's time 0. So one snapshot. Now we're going to put all of time, which equals, okay, it's going to be C1 psi. Where will it be or where it was? Exactly where it will be or where it was. Exactly right. Bingo. Right? We're going to say psi1 of x as normal. But now we're going to add in the time equation, which is E minus I E t, right, E1t over h bar, which is the pixels, plus C2 psi 2, that's psi, not phi, I made a mistake there, of x, and then E to the minus I second constant t over h bar. All right, so that's all we have to do. So we've now recreated that function, right? But we still don't know what these numbers are. But we've recreated the function, so we know that roughly how the function is going to behave. Okay. Now, okay, we know that the energy packets, these things are the energy packets of each of the individual waves. Okay. So all we have to do now is do this, right? We know that right, xt, we know that the absolute value of that squared equals 1, okay? Or the integral of that equals 1, sorry. So what we're going to do is we're going to square it, right? So the first thing we do, if you remember, by squaring it, it's actually going to shrink the whole thing down. Sorry, let me put my watch, yes, right? It's going to shrink the whole damn thing down, right? Now, we did this before. We said by squaring it, it actually shrinks it down. So what's going to happen, I'm going to skip the middle maths because that's for a mathematics lecture. That's going to equal C1 squared, right, psi 1 squared, plus C2 squared, psi 2 squared, okay, plus 2 C1 C2 psi 1 psi 2 cos, right, which is cosine, which is trigonometry, okay. And this was Euler who came up with this, that freaking genius. Okay, E2 minus E1, all right, T over H bar. All right, so basically we now know that this equals this. Okay, and that's from Euler's formula. Okay, that's it. So excuse me for a moment, let me just pull this down. Okay. So, jeez, man, this wind's getting too much. I'm stopping now. All right, so what we've done, right, we have now, by doing this, we've gotten this equation. So this equation's freaking awesome because it's gotten rid of the time, but the time is still in here. So we can now, if we know the location of the function, of the waves, we can actually solve it and figure out what the energy is and the time is. Okay? And we'll get an equation that shows the movement of time relative to the distance. So that mathematics actually allows us to predict where the phone was
or post-dict where the phone was and predict where it will be. Right? And that's the end of this lecture. In the next lectures, we're going to go further into time-independent equation, and it's going to get more and more and more complicated. I'm going to show you drawings, and we're going to do examples, and by the end of it, if you have some maths understanding, you should be able to calculate simple problems, and we're going to do some together. So, as always, Gabversity, where facts don't care about your feelings. And always remember to go fact yourself.